susceptibility of tuberculosis. And the last one with respect to chi-square is where the chi-square distribution is used in the case of testing of population variance. And if you want to test that a particular normal population has a specified variance, we set up a null hypothesis that H naught sigma is equal to sigma naught, and if x1, x2, etc., etc., it's a random samples taken of size n taken from a given population, then under the null hypothesis H naught, the statistic chi-square is equal to summation of xi minus x bar by sigma square. That is, xi minus x bar will be n into s square by sigma naught follows a chi-square by n minus 1 degrees of freedom. And if the n is greater than 30, you make use of a Fisher approximation, as square root of 2 chi-square follows a normal distribution with the square root of 2n minus 1 and 1. And you take the deviation of square root of 2 chi-square from 2n minus 1, it will be following a normal distribution with the standard, it will be following a standard normal distribution. Okay. And so this is the basic concept when you're testing the population variance. And let's take an example. You have a random sample of size 20 from a normal population, which gives a sample standard deviation of 6. Let's test whether the population standard deviation is 9. Substituting the values, you have the n equal to 20, your sample size, the sample standard deviation is 6, the variance is 36, your population standard deviation is 9, the population variance is 81, so sigma H naught sigma square is equal to sigma naught square, and H1 sigma square is not equal to sigma. So hence you calculate the chi-square as ns square by sigma square. Substituting the values, you get an 8.89. From the table, you have chi-square at 5% level of significance with 19 degrees of freedom. So n minus 1 is the degree of freedom. You get a 30.14 from the table. So hence your calculated value is less than the tabulated value. You can say that you accept the null hypothesis. You can say that the population standard deviation is 9. That is acceptable. Right. And when it comes down to testing the equality of two variances, when we assume that there is equality in variance that was made up using the t-test, and we are interested in actually comparing the variance of two populations, we make use of an F distribution, especially when you're having a small sample. Assume that we repeatedly select a random sample of size n from two normal populations, and consider the distribution of ratio of two variances, F is equal to S1 square by S2 square. The distribution that is formed in this manner by taking the ratio of the two variances of the samples that are being taken, it approximates to an F distribution. It's something that is, the distribution looks something that is similar to the chi-square with the following degrees of freedom. The F distribution has got 2 degrees of freedom, V1 which is N1 minus 1 and V2 which is N2 minus 1 with respect to the two samples. If the two samples are equal, of course V1 and V2 will also be equal. And the basic assumption is that the sample is being randomly chosen, the samples are independent from two normal populations, and there exists some kind of variability. And when it comes down to the table of F distribution is quite different from the others. There is for each level of significance, we have a different table. Normally, we make use of the 5% level of significance. You can find the others in the class tables. And the degree of freedom is across the rows and the columns that is being given. And of course, you have to, the first degree of freedom or the numerator degree of freedom falls across the columns, and the denominator degree of freedom falls across the rows. So how do you read it? Let's say that you have two samples with N1 10 and N2 7. Hence, the degree of freedom will be 6 and 9. If you're finding the F at 6, 9, okay, you're finding the F at 6, 9, the 6 should be from the numerator and 9 from the denominator. So 6 should be from the numerator and 9 from the denominator. That gives you a 3.37 as your table value. So at 5% level of significance. So you cannot make it the other way around. You take the 6 in the column I mean, yeah, 6 in the row and 9 in the column, you get a different value as a 4.10. Though they may be considered as quite close to each other, but still a 3.37 and 4.10 are quite different when you consider it in terms of calculating the uh, tabulated value or rejection region. Okay, so that has to be taken into consideration. And when it comes down to the hypothesis testing to compare to the two variances, you have your null hypothesis stated as sigma 1 square equal to sigma 2 square. And sigma 1 square greater than sigma 2 square or less than sigma 2 square or not equal to sigma 2 square. So all of them can be taken as the alternative hypothesis. And the F ratio is calculated as S1 square by S2 square, where S1 is the largest among the two variances. So it's the order in which the numerator is chosen is based on the size of the variance that is being taken. You reject the null hypothesis if the tabulated value is less than the calculated value. Otherwise, we accept it. So let's take an example. Yeah. The variability in the amount of impurities that are present in a batch of chemicals used for a particular process depends on the length of time that the process is in operation. Let's say that you have a sample of size 25 that is drawn from the normal population, which has to be compared to a sample of new process that has been developed to reduce the variability of impurities. You have two samples, one of size 25 and the other is also of size 25, and the standard deviations are given. And we want to test, of course, if there is no variability, we assume that there is no variability. So sigma 1 square is equal to sigma 2 square. Otherwise, the sigma 1 square has a greater variability than second one. Or with respect to the second one, the variability has been, that is some impurities or the variability, the length of time in which the process is in operation depends on the impurities that is there. Okay, new process is able to reduce the variability in the case of impurities. So we take the F statistic is calculated as S1 square by S2 square. Since 1.04 is greater, we'll take 1.04 divided by 0.51. You get a 2.04. And from the table of 2424, you get a value as 1.98. Since the calculated value is greater than the tabulated value, we reject the null hypothesis. We conclude that the variances are not equal and the variance of first one is of course greater than the second one. Or you can say that the new process has reduced the variability in the impurities. Okay. Coming into the last example, in a sample of 8 observations, the sum of squared deviations of the items from their mean was 94.5. In another sample of 10 observations, the value is found to be 1 or 1.7. Test whether the difference is significant in 5% levels. You have n1 equal to 8, n2 equal to 10, x minus x bar is given as you are given the sum of squared deviations, that is x minus x bar square is 94.5 and y minus y bar squared is 101.7. H naught at sigma 1 square is equal to sigma 2 square would be our null hypothesis, and h1 sigma 1 square not equal to sigma 2 square will be our alternative hypothesis. That is, there is no difference in the significance. So difference in the variability. So you have the degrees of freedom as 8 minus 1 and 10 minus 1, 7, 9. And when we consider, we can, of course, we can calculate the variances as sx square and sy square with the data that is given to us. You have it as sigma x minus x bar the whole square by n1 minus 1 and sigma y minus y bar the whole square by n2 minus 1, giving you respectively 13.5 and 11.5. So since 13.5 is greater, you take that to the numerator, and hence your degrees of freedom will be in the order 7, 9. From the table, you get the value 3.29. From the calculation, you get the value 1.195. Hence, since the calculated value is less than the tabulated value, it falls in the acceptance region. And we can say that the two variances are equal, or we can consider that they're both taken from the same population or they have similar variance. These are the basic tests that we normally do in the case of like the chi-square test is primarily used when you're having a non-parametric test, and the F test is basically used when you're testing the variances. We have seen that in the case of proportions and sample means, we make use of the teeth statistic, whereas when it comes down to comparing the variances, we go into the F statistic. Okay, that's all. Thank you. Happy learning.